Okay, thank
Let me quickly check. Yeah, it's recording.
Okay, thank you very much, Eric, for this nice introduction. Yeah, as already announced, the topic of my presentation is the increased use of scrap during steel production and the effects on microstructure and also mechanical properties. Um, at the beginning, I'd like to give you a small overview of the content, but before I do that, what I definitely have to mention, a lot of this work, of a lot of the results which I'd like to present, have been produced by two PhD students, which are acknowledged here. It's Lukas Hatzenbichler and Nicholas Kostrin, who are going to have the defense of their PhD thesis within this year. And also our senior scientist, Kiran Babusrika Kolabu, did a lot of, or contributed a lot to these results here. Okay, so the content of my presentation will be first I'd like to start with really 2 slides only introduction to Montana-Universität Leoben. Then I will try to outline the motivation of our work, and then I will jump into different topics. As it is intended to be here also a general lecture, I always try when I tackle these topics here to put a little bit an emphasis on the methods we are applying. For example, I've included here one chapter which is atom probe tomography, which we do a lot. So I will briefly introduce with 2 or 3 slides the method here which we are using, so that it's maybe interesting also for persons who are not familiar so far with the methods we are using here, where the results come from. Good. So first, small introduction to our university. We are located here in Leoben in Austria, within the mountains. We always say it's very little city. But it's the second largest in Styria. We only have 25,000 inhabitants. Anyhow, we say it's in the heart of Austria, in the middle of Austria. Nice surroundings. You can go skiing there. Also, from an industrial point of view, this is important, or it has some history, as the steel production process of the oxygen-based steel production process, Linz-Donowitz process, was developed together with the main production sites of first Alpina, Linz, and Leoben here, starting in the 1950s. And as there is iron ore nearby, it has a long mining tradition, our university. That's why in German it's called Montana-Universität, in English now Technical University of Leoben. Anyhow, where we focus, we have been founded 1840, so I'm already looking forward to be active, still active in that time when we have the 200th anniversary of our university. Our focus is in raw materials, processes, and materials. So we are saying we are close the loop. We also deal with topics handling recycling and so on. So to be really in the focus of circular engineering, as we start already, of course, from the mining field. We do have certain different fields of studies in the bachelor program, now also English ones available in the bachelor program. And all over, although we are a small city and maybe not the biggest university, we do have in the materials field, material scientists, working more than 500 material scientists here in Leoben, when you also take into account the non-university research institutes, which are normally always somehow connected to the university. Okay, so with that overview, I'd like to come to the motivation of my presentation today. And from the title, you have seen that we are dealing now with increase of scrap usage. And of course, the motivation for this work comes that in general, when one tries to use or reduce CO2 emissions, the goal or the solution should be that you do, instead of using coal, hydrogen as reduction agency in metallurgy processes. But however, this is not considered to take place within the next years. Maybe you are very familiar with it, that a lot all over the world, I would say, a lot of pilot plants exist where hydrogen is already used as reduction agents. But anyhow, as the availability of huge amounts amounts of green hydrogen from renewable sources will be not possible within the immediately next years. Everyone is aware that there has been some transition in between, and this CO2 reduced steel production has to be fulfilled via transformation from the classical blast furnace route, which of course emits huge amounts of CO2, to a shift towards an electric arc furnace production as one method with how significant reduction of CO2s can be achieved. It is important to point out, of course, it depends for the electric arc furnace production how your share, how your electricity shares. When it comes from mostly renewable resources, you can tremendously reduce your CO2 emissions compared from blast furnace to electric arc furnace production. And what comes into game then is that you can use higher mix of steel scraps, different steel scraps, the share can be higher. And then the big question is, what do increased tramp elements, what effect do they have on, for example, the microstructure, the nanostructure, and of course also maybe an embrittlement of your final steel products. Elements which are intended to be increased after this higher share of scrap is copper, chromium, nickel, molybdenum, cobalt, tin, antimony, arsenic. Of course, always important to mention, chromium or nickel or molybdenum are also alloying elements. And when it comes to low alloyed steel grades, where they are not intentionally alloyed, one can consider them also here as tramp elements. In general, the influence of these elements, which are again mentioned here, was investigated a lot decades ago. You will find a lot of literature what, for example, sulfur, phosphorus, nitrogen, hydrogen do cause in steels when they have higher contents. Now the huge but is that it is not known on newly developed advanced steels with complex microstructures where you have nano-microstructural elements incorporated which come from an advanced processing technologies. So the fabrication of steels and the development of steels within the last decades have been done on very pure, would say pure steel grades with very low content of these alloying elements. And now the big question is when these tramp elements are increased by using higher scrap rates, then what is about demanding applications for the automotive industry, for example, railway systems, or for the crane and lifting industry? Yeah? A profound knowledge about the influence of these different elements on the nano and microstructure is necessary, that the properties and performance of these steel grades can be used as has been done over the last decades. So when we consider further what effect such tramp and trace elements can have, of course, there can be different influences. One influence can be that they might have an influence on thermodynamic and kinetic properties. They can shift phase transformation, they can delay phase transformations, they can retard recrystallization behavior, for example, or they can have an influence on the microstructure. They can form precipitates, unwanted phases can suddenly occur. They might have an effect on the grain size, or they may result in segregation on different boundaries within your material. In order to investigate these effects, one needs, of course, to consider first what element contents we are talking. And what you can see, for example, is production from blast furnace, here production from electric arc furnace. And you can see elements which are not intentionally alloyed, chromium, nickel, molybdenum, and from thousands of chemical analyses, you can see approximately content which is here after blast furnace production, and you can see the increased levels which results when you have high scrap rates using electric arc furnace production. So that means one can really expect an increased content of chromium, nickel, molybdenum. And the same is true for copper, tin, and cobalt. And these elements might be critical if they are not, as already mentioned, intentionally alloyed, and if they are not easy to be removed from a metallurgical process point of view. I do have to point out that I'm not the expert on metallurgical processes, and this talk will also not focus on how to avoid or how to reduce the amount of tramp elements during production. One well-known example is copper, which can be not easily removed or even not removed. And there are also other elements. Some are harder to be handled, some are cost extensive if you want to reduce them, and some are more easy to remove. But as I said, I will not focus here on the metallurgical processes. I will focus here, I belong to the Department of Materials Science, so I will focus on the micro and nanostructure and then the influence on the possible influence of the mechanical properties. Good. So with that introduction, I'd like to come to the next chapter, which is then alloy design we have done and microstructural characterization. So what we normally do is that we do a laboratory trial alloy melts, then investigate the microstructure property relationship, and then try to answer under what conditions and contents are the tramp elements can be critical for steel properties. And what we always aim for is to do that on a scale bridging attempt. That means we start here with the trial alloy production, including as close as possible to the industrial process, then do mechanical properties, go on the microstructural level down to the nanostructure of the material. And what you can see exemplarily is shown here, a trial alloy set, production of trial alloy. In that case, it has been a 51 chromium 4, vanadium 4 alloy, quenched and tempered steel with medium higher carbon content, I would say. And what we did here is we added intentionally different contents of different elements. And then finally, of course, to be able to investigate what do these elements cause on the properties. We did this also for different steel grades. You can see one variety, one selection here, I would say. You can see that we did this from the very unalloyed side, which is a more or less pure ferritic with a little bit perlite fraction microstructure, up to an alloy with 100 chromium 6, also a well-known alloy from the application for bearings and also other applications with a very high carbon content, 1% alloyed with chromium. So that means with definitely higher hardness and overweight activates microstructure, fully perlitic, and also here in between some different steel grades. And what we did is we always had some contents here, as shown here, some carbon content, manganese, silicon alloyed, then increased these different tramp elements here or added them intentionally. And most of the time we defined the reference alloy, medium level alloy, that means to simulate medium scrap levels, and high level alloy, high scrap level alloy. And here you can see a microstructure for that example here, 0.6 carbon. After hot rolling, you can see, or in the delivered state after rolling, you can see here a perlitic microstructure with some ferrite on the grain boundaries. And when you compare that example here in light optical microscopy, you can see that it's always, I would say here, perlitic microstructure with some ferrite fraction, but I guess no one could distinguish here that something specifically has changed here regarding light optical microscopy. So in all cases, we have a perlitic microstructure with some certain amount of grain boundary ferrite. When one wants to continue to investigate the influence, if there is an influence coming from that different elements added here, one can also perform high temperature laser scanning confocal microscopy. By applying that method, you can use some specific temperature time profiles here, and what we have available is this high temperature scanning microscope within our lab, and you can see that you have here is the oven, the chamber. You insert your sample here, which is in the size of, let's say it can be a square of 4 millimeter in diameter, and you heat up your sample with this lamp here. And what you do, you scan your sample by a laser, and then you get an in situ image during the time temperature heating. And compared to that, normally you are able to see the microstructure, ferritic, perlitic here after the heat treatment or before. But with that device, you are able to record your image during the temperature time profile, and you're able then to also investigate, for example, your microstructure at a temperature where you are in the austenitic phase field. And by doing so, then one gets an idea during cooling how the phase transformation process is taking place. And of course, when the images or the videos are evaluated at the high temperature, you get information about your austenite grains. And for giving you an example, I'd like to show again, coming back to that example here. For reference array, medium scrap level, high scrap level, one can see here now the images or the videos starting. You can see the temperature. We do heat up here. Maybe it's hard to see, but now we reached 1100 degrees Celsius. So we're in the austenitic phase field now. You can compare the three microstructures if you want to. Then we do holding 10 minutes, and then we're already cooling down and do see the displacive transformation to martensitic binitic shares or volume fractions, which are here the highest compared to that one. And by that you can get information when you do then an evaluation about the grain size, about the maybe also at least an impression on the phase fraction of martensite or austenite. Maybe I will show the videos again, as it is always quite fast, I would say. So, okay, we have the three variants here. We do heating up here now. Now we are reaching the 1100 degrees C. We do holding for 10 minutes. One can see the austenite grains. When you have a close look, you can see twin boundaries in between also. Here, for example, the austenitic phase field. And now we're already cooling down, and you can see now suddenly the transformation to displace the phases. Let's call it simple martensite binite. It's of course it's hard or not possible to distinguish what the share if it is binite or martensite. But what you can see already here with increasing tramp element contents, you can see that you do get a higher share of displaced phases, and maybe it was not easy to see, but the austenite grain sizes changes for these three alloys. And to evaluate that, of course, one can take images at the temperature of 1100 degrees C, and you can then do a grain size evaluation when you see these three images, and that was done here. Python scripts has been used. You can see colored images where the grain size was evaluated, and you can see the distribution of the grains here. And for example, what you can see here is that with this increasing tramp element contents, you get smaller grain sizes. Yeah, the green curves here correspond to high level of tramp elements. Here's evaluated the ASTM grain size, which is higher. That means smaller grains are present here, a higher share of smaller grains we have with increasing tramp element contents. You can see also here grain diameter for the three alloys. And what you can see is with the increase of tramp element, smaller austenite grain sizes. And you can see here big standard deviation, of course, but in general, we have seen this on different alloys that with increasing tramp elements, smaller austenite grain size can be expected. And this can be attributed to solid track effects on the grain of tramp elements on the grain boundaries, which hindered the grain growth behavior. In order to further investigate the phase transformation behavior, one can also, of course, do conventional dilutometry. That means you apply heat treatments on your samples and measure the length or the change in length during this heat treatment. And by doing so, you can, of course, do the same variations as we did before. You can have some specific austenite temperatures, and you apply different cooling rates then to it. And when doing so, you can again investigate the influence of the increased tramp elements. And what you can see is, for example, here, with a higher share of tramp elements, the phase transformation temperature is shifted to lower temperatures. So there is an influence of the tramp elements on the phase transformation temperature. It is retarded by higher tramp element contents, which can be seen here. And when one is doing the whole CCT diagram, continuous cooling transformation diagrams, also called TTT, time temperature transformation diagram, one can see here that you have again here the different contents, the reference alloy, medium scrap, high scrap alloy, and one can see that suddenly critical cooling rates, which define the area where martensite is formed, are suddenly changed. And what you can see here, for example, with increasing tramp elements, slower cooling is necessary in order to get a martensite-free microstructure. For example, when that is important, you can see here the numbers, and you can see the critical cooling rate is decreased. So that means some phase transformation temperatures are changed by the influence of these tramp element contents. And for example, as I said, this critical cooling rate here, which defines the cooling rate where you go below where you get a martensite-free microstructure. And when that is an important topic, then you need to slower cool your sample afterwards when you want to avoid martensite or bainite in your microstructure. And to prove that it's really that is really the case, you can see here again images from light optical microscopy. You can see here again a palitic microstructure with ferrite on the grain boundaries. And suddenly, when you have higher shares of tramp elements, you can see that you find these displaced phases. Of course, it's hard to see here, but you have to believe me that when one uses also higher magnification, reference medium, high scrapular, you see just more such areas which are then martensitic or painitic within your microstructure. When, of course, you apply the same cooling rate to your samples. And to show you that in more detail now is here the high level alloy. Here is that area where you have these displaced faces. And here on the ICM, you can definitely see here martensite, perlite, and bainite. You can see carbates here in between the bainitic sheaths, and also the proof here via EPSD. And here martensitic areas, bainitic areas. And what is also important to mention, what we discovered is that not only martensite can be found, what often goes along with martensite, we did find small islands of retained austenite, which have been not present when compared to the alloys with the low tramp element contents. Yeah, so it's a mixture then of perlite, martensite, bainite, and some share of retained austenite can also be present in the alloy afterwards. In order to investigate that into more detail, we also performed high energy X-ray diffraction using synchrotron radiation. We went to Hamburg in Germany, where we have access to use high energy X-ray diffraction. I have to acknowledge another PhD student here who's working on that topic. It's Marek Gocnik. And what there is available, a dilatometer can be placed within the beam line. So the beam hits the dilatometer here, and the sample is, of course, inside the dilatometer. Here is the detector, and that means you can do in situ heat treatments and get an information about the phases which are formed depending on the applied heat treatment. And then again shown here, such a temperature profile, 1100 degrees C. So that means here's the temperature, here is the time. We are heating up, holding for 10 minutes, and then we are cooling down. And what one observes, or what one can observe here, is then the development of the different phases. Can nicely see here, first we have the ferritic phases, of course, then here, of course, in that time frame, we are in the austenitic phase field, and then again, after cooling, we do have again our ferritic microstructure. So that's the reference alloy. And then when you do have the medium or high level tramp element contents alloy, what you can see here is that, I hope you can see it here. I'm looking for it's hard to see here. You have still austenite peaks available after cooling down. So that means retained austenite in the high level alloy is increasing. And I will show you then a much more detailed analysis, which is shown here. Here you can see the diffractogram, maybe you're used also to it. And you can see, for example, here, that is the 200 austenite peak, and you can see that this is increased compared to here. Here would have to be the 200 austenite peak, and when you compare the reference alloy to the, let's say, tramp element content, you can see that when you evaluate that with Rietveld refinement or whatever you are using, you get to a share of 1.5% retained austenite, which can, of course, have an influence on your mechanical properties. So you see the influence of tramp elements. You can investigate the influence on tramp element during the heat treatment and also in the final state by applying such methods. Yeah, retained austenite fraction increases with the tramp element concentrations, as we have this higher displacive share, this higher share of displacive phases like martensite and bainite, and so in the end also this higher share of retained austenite. What we did further, we investigated the influence of these tramp elements on the palitic microstructure. Another PhD student is working on that. It's Clement Winzeli, also acknowledged for his work in that field, because he used machine learning methods to evaluate the microstructure. You can see here an SEM image of a palitic microstructure. We divided the microstructure, the palitic morphology, I would say, into parallel, broken, or we called it degenerated perlite. And what we did here is, first of all, you have to do manual image annotation using a software then called RoboFlow. You need this training set, which are manually annotated. These images, we did it for 120 images. That means that you machine learn your software, that it's able to detect that what you want him to say is parallel, broken, or degenerated. And then instant segmentation was done with this machine learning model, which is called YOLO, you only look once. And this evaluation brings then statistic relevant, I would say you're able then to produce statistically relevant evaluations when you apply this to ferritic paletic microstructure. And what we have seen here also is, for example, that the area fraction of perlite, here again for a base alloy and then a trial alloy with increased tramp element, and I only like to focus on this broken perlite. So the assumption that maybe these tramp elements might have an influence of the growth of the perlite lamella seems to be true, as we have evaluation of really a lot of images have been done with this approach then, and you can see that the phase fraction or the fraction of this broken perlite increases with increasing tramp element contents. Good. So when one does a lot of these investigations, one asks then, of course, about how the mechanism is changed of the phase transformation. And of course, one can do first thermodynamic calculations using, for example, thermocalc. You can see here reference, high-level alloy, and you will not, depending on the available databases, you will not see really an influence. When one has a closer look on the chemical driving force, which is shown here, depending on the temperature, again for a reference and the high tramp element alloy, you will see that there is no difference. The same is true for the interface energy, and where one can see that one cannot really appropriate do the calculations for the phase transformation temperatures for ferrite or perlite. What has to be done regarding this this Calvert method, calculation of phase direction, you do have to adjust your grain boundary energy. This was done here in that case for reference, medium scrap, high scrap level alloy, and then suddenly your simulation results will fit to your experimental values. And the idea behind was to adjust this this grain boundary energy, that the tramp elements are located on the grain boundaries, and on the grain boundaries that result in a lower grain boundary energy, and therefore these tramp elements suppress the perlite nucleation, and that means then you get more easily these displacive phases, martensite and bainite, which forms during the transformation. And when you do not have that content of tramp elements, you do have higher grain boundary energy, which is here the case, and then you get your growth of the perlitic phase. So that was the idea behind, and just to show you here, are shown ferrite start temperatures and perlite start temperatures from the CCD diagrams I showed before, and you can see in the different colors here, always the results from the dashed lines are the ones from experiment, and the full lines are the ones from modeling. And when you adjust this grain boundary energy, in the end you can then see that your ferrite start temperature and your perlite start temperature does fit to the one you have measured. Yeah, then you get a direct, nearly perfect fit. That means grain boundary energy, the conclusion was grain boundary energy is somehow changed by the tramp elements. Good, then I will come to the next topic, which is temper embrittlement. I'd like to change again now here the steel grade we have investigated. Again, the question, under what conditions these tramp elements can be harmful to the steels in the three main fields, heat treatment and also influence on mechanical properties. And we did it again on a 51 chromium 4 vanadium 4 alloy. Application for that alloy is manifold. It can sequential tempered steel, can be for the automotive industry, for example. And what is very important for that kind of alloy, you do, of course, heat treatment, which consists of a hardening process, and afterwards you do a tempering process. And during this tempering, there is some tramp elements very well known since decades that they can cause temper embrittlement. And in order to investigate that more into detail, we did tensile testing on that alloy. Here is shown the tensile strengths for different alloys where different elements, different tramp elements have been added. And what you can see here is different tempering temperatures. And what you can see here is almost no significant change in the strength level. I would call it more or less constant. We didn't see any influence. But anyhow, when it comes to notched impact testing, and let's focus here on the highest tempering temperature, 650 degrees C, which is a tempering temperature which might result in temper embrittlement, and we really observed it here by adding these different elements. One can see a decrease here in the notched impact energy. Yeah? And of course, what is also important to mention, the heat treatment temperature is very decisive. When you have lower heat treatment temperatures here, this star-like dots correspond to 450 degrees C. You can see almost no influence, I would say. And the higher the temperature, the more pronounced is the influence. And now the next question, what is the reason for the loss of the toughness, of course? In order to clarify that, we did again microstructural characterization, performing SEM, for example, using SEM and EBSD, electron backscatter diffraction, evaluated grain sizes also here. And in that case, when you compare the alloy on the very left side, the reference alloy, and the one on the right side with the highest contents of tin and antimony, in that case, you can see there is almost, or there is even no difference in the grain size. Here are the mean values, here's the distribution of the grain size. And also from EBSD evaluation, one would say they look very similar. Also, when performing scanning electron microscope imaging. That means we had a closer look on the carbides that might form during tempering or that form during tempering. Here it's cementite, ferrorized cementite at 650 degrees C. Again, high energy X-ray diffraction have been performed here using synchrotron radiation. And when one has a closer look, just focus here on the phase fraction of cementite here, which precipitate during the tempering. One can see there is almost no difference between the two, the reference alloy and the one with the highest tramp element contents. And also, when you have a close look on that images, you can see no change in the microstructure. No change in the microstructure was observed that could explain this loss in toughness. So then, when one asks the question, what is causing then, what is the causing reason for that decrease in toughness? One can look on the fracture surfaces to see if it is really the case that one sees on the fracture surface, a ductile fracture here, and it was the case here for the highest content of tramp elements, where one can see that these tramp elements result in a shift, which can be also seen in the fracture surface from here to here. That means from ductile to brittle to a higher share of brittle fracture, and also intergranular fracture was observed, as can be concluded from here. So that means in the end, yes, it seems really that something is changing, which we cannot see by using standard microstructure characterization. Again, to summarize, strength is the same, but loss in toughness. So what can cause this loss in toughness but not in strength? And there are possible causes. You can have precipitates during the tempering, or you can have segregation of elements. And when it comes to segregation, we perform atom probe tomography. We are in the lucky situation that we do have a machine available at our institute, and I'd like to go into details here. And again, as I said at the beginning, maybe give a very brief introduction to atom probe tomography. And yeah, it's the machine we have available here. What you need for performing APT is you have to prepare your sample in the shape of a tip with a radius of below 100 nanometer. Then you use very low temperatures and then a very high vacuum conditions you need, because you do then field evaporation of ions from your tip. And to achieve this field evaporation, you use either thermal pulses by laser or voltage. And when you then do your first of all, when you then do your reconstruction and you investigate the, you register your atoms which hit the detector here, you get information about the position. And what you do is you measure your time of flight of individual atoms or ions which are detected. And then in the end, you get information, a three-dimensional atomic information of your measured sample volume. The big task is to prepare your sample in the shape of a tip with a few below 100 nanometer, few tenths of nanometer. And that can be done in different ways. For example, you can use a 15-second laser machine where you prepare your microtips first by using this laser. You can see here several tips which have been preferred. And of course, then you need a focused ion beam machine where you can mill or sharpen your tip in the end. You can then perform transmission Kikuchi diffraction. That means EBSD in transmission direction, so that you get information about the orientation on some specific areas. And I'd like to show only this example here. You have to have you have here an SEM image. You can see, for example, that might be a high angle grain boundary. By performing EBSD, you get the information that yes, that's really a big misorientation between these two grains. And then you can be sure if you locate your tip or extract your tip from that position by doing on the focused ion beam some protection methods, and also always try to have your prior austenite grain boundary in your image present when you do the final milling. And in the end, you get then a sharpened tip, which can be measured by atom probe tomography. And I will not go into detail here, but what you simply have to then take into account when you do your measurements, how the device works, is you have a potential and kinetic energy of your released ions, and by solving that simple equation, you then come to the mass to charge ratio of your elements. You measure the time of flight, that's the time of flight, and you get then in the end your spectrum. That means you get a mass to charge ratio. You can see that here is a logarithmic scale, and for example, when you know where your iron peaks are, you definitely know what atoms you have measured. For example, here are the molybdenum atoms. Yeah? And when evaluating such things, you get then information, a three-dimensional nanoscale information about your elements. Here is shown one example of carbon and boron. When one is then doing 1D concentration profile analysis, for example, you can see enrichment of carbon on a triple boundary here, or also boron, for example, on that boundary here. You can evaluate the contents of the elements you have on the boundary and so get information about the segregation behavior of the different elements. Okay, with that I'm done with the introduction of our measurement principle of atom probe tomography. Now I will tackle the last chapter, which is the segregation of elements. So coming back to this example I have shown before, the impact energy, the decrease of the impact energy for the different added tramp elements here. And to answer the question if there is any segregation present, one can see here a measured atom probe tomography volume. You can see here a boundary, a grain boundary. You can see here a cylinder which have been positioned for evaluation, and when one investigates then the 1D concentration profile, you finally get to such numbers when you can see these interfacial accents. The unit is atoms per square nanometer on the grain boundary, and you can see that for 650 degrees C, which we had before, this tempering temperature, and you can see it for different elements here. And you can see, for example, there is a significant segregation of tin and antimony. You can see green is tin and blue is antimony. And here, the reference alloy, here the one with the highest tramp elements, and you can see that this content is definitely increasing. For copper, limited segregation was detected, and what is important to mention here, you can imagine that, or you know that atom probe tomography is very time consuming, and evaluation is always not that straightforward, but anyhow, any measured dot here represents one ABD measurement. So that means a lot of data were generated in the sense of ABD, which is a very local method. But when one takes the average values, one can see this increase in these different elements. And also for carbon, carbon is well known to segregate to grain boundaries, atoms per square nanometer on grain boundaries for carbon. And here you can see it for phosphorus. Yeah? And the reason why copper is not seen that strong segregating in this kind of alloy is that what we have seen next to, for example, cementite, which we also measured here in a volume, is that copper already forms at very low contents clusters. It's well known in iron that copper is clustering, and that's why we do not see that strong segregation density anymore. And when one investigates the chemical composition of that copper precipitates, it's also nice to see that copper can act somehow as sink for this tin and antimony. You can see the enrichment of copper within the yellow, the orange curve corresponds to copper within this measured volume. And what you can see is an increased tin and antimony content also within the clusters. And now the highest level, at least for me, is always density functional theory when it comes to calculations and to compare these calculations with experiments. And what you can see here is calculated segregation energies and cohesion, change of cohesion on boundaries, and the work of separation was calculated here. And first of all, I will not go into detail here, but I want to point out is that segregation density and impact on cohesion seems to correlate somehow, and there is a strong influence on the calculated type, grain boundary type. You can see different grain boundaries, a different type of grain boundaries which have been calculated. And what you can also see here is, just have a look on the color content, arsenic, antimony, and tin. As they have a very high segregation energy, that means strong segregation tendency, they do have also a strong influence on the work of separation. That means they tend then to result or cause intergranular fracture. So that fits together. And in general, according to these calculations, arsenic, tin, and antimony are one of the strongest elements showing segregation tendencies. And now the question is, how applicable are these calculations to complex alloys as we do have in steels? And one or what is important to mention is one should always consider here the bulk concentration. So our attempt here was to use the interfacial access from atom probe tomography I have shown you before, atoms per square nanometer, and divide this by the bulk concentration you do have in your alloy. And when you do so, one suddenly comes from here to this diagram here. And what you can see here, that suddenly, as phosphorus didn't have the high bulk composition, you can see phosphorus do have a very strong segregation tendency. Also, antimony and tin. Compared to that, copper and nickel do not have that high content, that high segregation tendency. And to even compare that with the results from density functional theory, we developed that diagram where you can see the segregation energy, and you can then group your elements into two fields. You have here this, what I shown before, segregation energy, segregation ratio dependent on the bulk composition, and you can see here elements which are known to be substitutional in your lattice. And you can see there is more or less a linear correlation. That means an element causing strong segregation from DFT calculation measured also the same behavior by atom probe tomography. What is not true is this linear trend for phosphorus and carbon. And that can be explained as these elements occupy interstitial sites. From carbon, it's well known. Phosphorus, also some calculations have been formed, which are shown here. I will not go into detail, but with that calculations, it's a matter of debate if phosphorus is only on interstitial or substitutional sites. According to that calculation, they can occupy both. And so that's why these two elements do not cannot be explained that straightforward as these elements here do not have the strong linear behavior compared segregation energy to that measured segregation ratio. Okay, with that I'm in the end of my presentation. I think quite good in time, as I said, 45 minutes, maybe a little bit more. And with that I'd like to try to give some conclusions. I tried to show that increased tramp element contents can promote martensite formation, and some phase field transformation temperatures are shifted to longer times. That means critical cooling rates can be changed with increased tramp elements. You do have you can have different perlite morphologies. Then decrease of phase transformation temperatures I already mentioned, and you can have smaller prior austenite grain size due to solid drag effect by tramp elements. And then, of course, there can be an influence on the embrittlement behavior of certain alloys when it comes to certain tempering processes. And definitely tramp elements will cause segregation on will result in segregation on grain boundaries, and thereby infecting in the end the mechanical properties. And with that, I'm the end of my presentation. I'd like to thank you for your attendance, for your attention, of course, and I also have to acknowledge my funding agencies here in Austria, and of course my industrial partner. With that, I'm in the end, and like hand over to Eric again.